Welcome to Breadboarding. This is video 18 in the Nanocomp 6809 series. The Nanocomp 6809 is a design based on the 1981 Wireless World magazine project. And in videos 1 to 17, I built out the original Nanocomp design on breadboards, and then they extended it to add some bus buffers so we could actually drive more chips than the original design. We expanded to more RAM, more ROM, and we added a serial interface that was capable of doing about 57K, which we used to load programs from PC down into the Nanocomp. Then we went off and looked during videos V1 to V13, of which some of these videos were actually broken down to multiple parts. There's more than 13 videos. We built a breadboard video controller supporting VGA output, and that included support for a character mode, which would be 30 by 80 lines at 60 Hz, or 25 lines times 80 columns at 70 Hz with 16 colours, and we showed converting a Tetris game to actually run on the Nanocomp using that character mode. Then we extended that to do a high-res graphics mode of 640 by 480 pixels with 2 colours, and then we showed how to convert a Lunar Lander game to run under that. And then the final round of videos was to do the high colour graphics mode, which was 320 by 200 pixels but with 256 colours, and that was from a VGA palette of 262,000 possible colours, and we showed how to display the Doom title screen. If you want to find out more about those, there are 2 playlists that I'll actually include in the description below here, and you should be able to go through those and catch up on those if you want to see what's going on there. What I want to do now is to look at additional upgrades. So this is sort of an approximate order that I was thinking of doing this thing. So the first thing we're going to be doing this one is adding support for a full keyboard. At the moment we just have a 25 key keypad which we built on some strip board, which is fine for sort of basic use, but really need a proper keyboard. Then I'll be looking at adding a sound chip with also a digital joystick, so how to convert an analog joystick to provide digital signals. Then look at upgrading the CPU from the current 4 MHz version to the faster version, so that's the 68B09. And also, because that chip doesn't have the built-in clock generator, we're going to have to add some of the clock timing circuits to generate some of the necessary signals for the CPU there. Then this number 21, I was interested in looking at how to access hard drives, in particular a SATA drive with an IDE adapter or an SD card with an appropriate adapter. I'm not sure how practical this will be. I think we'll be able to access the hardware, but writing all of the software necessary to be able to read, say, a DOS file system, a FAT file system, I think may be a bit too much, but I wanted to at least see whether or not we can interrogate the drives and get the status and at least read a couple of blocks off the drive so we could show that if we wrote the software, we'd be able to access hard drives. Then in a number of videos I've mentioned the snow that you get on the video output, or the interference when the video RAM is being accessed by the CPU at the same time that the video controller is also using the RAM. So I'd like to spend a bit of time working out how to fix that. And one of the reasons for upgrading the CPU is that the faster CPU should make it easier to sort the timing out so that the two can slot in and not actually interfere with each other. And then finally, I'm looking at rewriting the current Nanocomp monitor, which is in assembly language, and rewrite that in C. And I'll explain why I was wanting to do that at some later videos. The basic Nanocomp monitor is very simple and straightforward and can use with a keypad, and so in future designs that might be quite a useful sort of basic sort of operating system to then build out a more sophisticated operating system from. But writing that in C will allow me to incorporate some of the recent enhancements like the VGA palette selection and all that sort of stuff. So that will probably be going on in the background during this period of time. Let's go and have a look at why you want to do this for the keyboard. So the existing keypad was created in Video 8 and consisted of 25 key switches and caps plugged into a strip board or Veroboard, and they cost around about £25 in total, I think, with all the key caps, the labels and everything else. I wanted really a standard sort of 102 plus key PC-like keyboard. Now, to make one with 102 odd keys was going to cost quite a lot of money, and to be perfectly honest, even if you bought proper key switches, making a PCB, drilling it out, all that sort of stuff, and making sure it fit will be a major project in itself. I looked at possibly using a modern USB keyboard, but really that needs USB drivers, and realistically you'd need to install a modern microcontroller to be able to do USB. I was trying to keep to 1980s and 1990s components, avoiding sort of 21st century components. To be perfectly honest, if you wanted to use 21st century components, you should just get a Raspberry Pi and run an emulator. Would probably be a much easier way of doing all this sort of stuff, but that wouldn't actually allow me to understand and work out how all the hardware works at the lowest level. So then looked at the original PC, PCXT and PCAT keyboards, but they're quite expensive and difficult to get these days. But the IBM PS2 keyboards that started to come out around 1987 onwards, and with a standard probably up until about 10 or 15 years ago, and they're still available on Amazon. In fact, I happen to have one that I bought last year, which is about £20, about $25, and there are still PS2 compatible keyboards available on Amazon. There are some which advertise as PS2, but you're really just a USB keyboard with an adapter, and I'll try to see whether or not a USB keyboard with an adapter will work as well, so we'll have a look at that. Now, I'm not going to go into too much detail about the low-level mechanics of how the PS2 keyboard works, because Ben Eater has done a really good video, a couple of videos on explaining all this low-level signals and how the PC keyboards return scan codes to tell which keys have been pressed and which keys have been released. And I'm not going to reproduce that there, but needless to say that Ben Eater's videos are generally very good and very informative, and I'd recommend you have a look at it. It sort of takes you all the way through looking on the signals and how you might want to interface with it. So the IBM PC keyboards, as I was looking at this, I went back through some of the documentation, and there are a number of sites which I'll include in the description below that include a lot of the technical reference documentation for the IBM PCs. One of the things I would say, the IBM documentation was very thorough and actually documented an enormous amount of detail, and included the sort of logic schematic diagrams for most of the models. So the original PC, which was released around 1981, this had an 83 key keyboard with an old style 5-pin DIN connector. This was a larger connector, and its keyboard interface used the 8255 peripheral parallel interface adapter, and it also used this 74LS322 shift register. So in Ben Eater's video, I think he uses a more recent 74HC595 shift register, but this was the one that was used on the early PCs. And the PCXT was very similar, almost the same. Then when the PCAT came out, there was support for the original keyboard, although it's slightly different and incompatible, and also an enhanced keyboard, the 100 and 102 key keyboard, which we would now recognise as pretty much the standard PC keyboard. But this still had the 5-pin DIN connector, although the internal electronics was much closer to today's, in that rather than using these two chips above here, it used the Intel 8042 microcontroller, which is the electronics which is in the majority of keyboards these days, although derivatives of it. And then finally, the PS2 Model 80, which I've been looking at, in particular the earlier PS2 models, also had the enhanced keyboard, but also now introduced the PS2 6-pin mini DIN connector. So this would be the green or purple connector that you'd be familiar with from PCs probably from 20, 25 years ago up to probably about 10 years ago. What we're going to be looking at doing then is using the PS2 and using this Intel 8042 keyboard controller to access the keyboard. So we're going to use a standard PS2 keyboard, trying to find an Intel 8042 microcontroller with the original keyboard BIOS is quite difficult to find. I didn't try very hard, but I suspect it will be very difficult. However, there was a VIA VT82C42 40-pin DIP keyboard controller chip, which was released in the 90s, and although it's sort of probably mid-90s rather than early 90s, these are available for about £3 to £5 on eBay, so I bought a couple of those, and in fact they were actually cheaper than the chips that Ben Eater was using in his project, in that I was using LS Logic and he was using HC Logic. The LS Logic versions of those chips were about 2 or 3 times the price of these keyboard controllers. The datasheet on this keyboard controller says it's a compatible direct replacement for the Intel 80C42 BIOS version of the keyboard controller, but it's entirely implemented in hardware logic, so it's fast, and it also does support PS2 mouse support as well. Now, I'm not going to bother with the mouse at the moment, but it might be interesting to see if we can get a mouse working in the future. Now, the Intel 8042, as I said, was used in the PS2 series and also in the compact Pro 386, which is really one of the first clone PCs that defined the standard for most clone PCs not coming from IBM. The key thing about looking at all the pinouts for all these things, this is the socket pinout and it's looking at the socket from the front. So you've got to be careful that you don't get the pins reversed. So here's the PS2 keyboard I got off Amazon a year or so ago. I couldn't find this exact model. They're about £19-20, and if you look on the back here you'll see it's quite difficult to tell here, but the only way really you tell whether it's a USB or a PS2, there's a tiny little tick in the PS2 interface here, and this keyboard in fact comes with a PS2 connector on it. So it comes with the original PS2 connector on it, whereas there are other keyboards such as this one here. This one didn't come with this connector, this is one I already had, but this is a USB keyboard, and these types of connectors will theoretically convert into a PS2 keyboard if the keyboard supports it. It's quite likely the keyboard does support it, but I haven't tested it yet, so we'll try that out in a little bit. So now I was doing my background sort of reading on this to try and understand how keyboards work, then I was looking at all the original IBM technical documentation. I'll include the links in the description below. But this is the logic diagram from the actual internals of the keyboard from the original PC from around 1981. I think this version might have been from 1983. And what this shows in the logic diagram is this is the keyboard matrix here, so this is the switches, and you can still see there's a load of matrix of drivers going here, and there's an output here that says whether or not we've got a key pressed, and then that goes to this. So this is where all of the outputs to the matrix driver circuit goes, and this is actually the connector to the PC. So the actual keyboard has an Intel 8048 processor inside it, or microcontroller inside it, and this is actually what's producing the clock signal, the data out signal, data in signal, and I think there's also a reset. The original keyboards actually had a reset signal here. One of the interesting things about this is that these signals all have pull-up resistors, and when I was first looking at keyboard, I thought my keyboard was dead because I couldn't get any signals out of it. What you need to remember to do is to include pull-up resistors, otherwise you won't actually see any signals when you're looking at these things with oscilloscopes or logic analyzers. The original PC keyboard has a microcontroller in it. So this is the interface from the original PC, and it's a little difficult to see, but basically this is an 8255 parallel interface adapter, and in addition to talking to the shift register used for the keyboard, this also has all the sort of dip switches and things where are the configuration options, and also is used for outputting speaker data and various other things. But the key thing really here is this 74LS322 does most of the serial to parallel and parallel to serial, and there's a couple of extra gates around here. I think this is to do with dividing the clock signal, and you can sort of see there's the output there. So that was the original PC. Again, probably Ben Eater's video, if he was trying to reproduce this according to the original PC, then this sort of circuit here would be closer to what you would want. So then I had a look at the PC-80. So the PC-80, although it still used the old keyboard connector, it did actually make use of the Intel 8042. So in actual fact, the PC-80 was incompatible with the original PC keyboards because it was making use of the new style, although the connectors and the were still the original larger 5-pin DIN ones. Then I also looked at the Compact Desk Pro. So the Compact Desk Pro, let me just make this a little bit bigger. This was probably the first sort of clone PC. This is a 386 PC, and this probably established a lot of the standards that were used by most PCs other than the IBM ones going forward. And so this actually uses the 8042, and you can sort of see some of the open collector buffer chips and things are out here, and obviously these had chokes and things on some of the inputs to protect some of the circuitry, but basically this has a lot of the stuff that we'll see in the other diagram. And then Finally, if we look at this is the PS2 Model 80, and again this makes use of the 8042, and you can see when we look at some of the other diagrams, you'll see there's 4 open collector inverters used and some pull-up resistors and a couple of capacitors, and you'll see that this diagram will be very much familiar when we look at the data sheet. So if we just have a slightly closer look up here, so you can see a lot of the pin outputs and things here are similar. There are a couple of pins which are being used for interrupts and various other stuff that I won't bother with on the 6009 to start with. And one of the things that we'll see in the controller chip is that the controller chip determines whether it's working in PS2 mode or in original PCAT mode, depending on the signals it gets backup power on from various outputs here. So depending on whether there's inverters or not, then it's able to work out whether it's a PS2 keyboard or a PCAT keyboard. So I'm going to base the design of the keyboard controller pretty much on the IBM Model 80 here. So this is the data sheet for the 82C42 keyboard controller. As I've already said, this is a hardware replacement, so I don't think this is a programmable microcontroller. This is actually programmed to do the PS2 keyboard and mouse support. It's a little confusing. I'm not going to go through all of this here, but the only thing to be wary of here is that the P23 and P27 do not refer to the pin numbers. They're actually the labels. So it's port 2, input output 3, port 2, input output 7. So that's something you just have to be wary of. And this explains how the chip determines whether it's in PS2 mode or PCAT mode, depending on how things are connected. And it's all to do with the self-test and everything else, and explains how it actually works. And then the key thing really that we need, we'll come back to this data sheet as we do the programming stuff, but this diagram really here shows how it's able to determine the difference between a PCAT mode and PS2 mode. And really the difference is I think it looks at, puts a signal out on I think 26 and 27, and it listens to test 0, T0 and P10, and if it's inverted on P10 then it knows that it's a PS2 mode and not this one. So this is the way how the chip understands what's going on. And these outputs here are again open collector, so they're inverters but they're open collector, so it means that you need a pull-up resistor to be able to see any signal coming out of there. So in order to connect to the PS2 keyboard we're going to need a connector. Now these are the type of mini DIN 6-pin connector, and if I just zoom in down here we'll be able to see a little bit better. The only thing about this is a little bit awkward in that in plugging this into strip board you've got 2 pins very close together here. So in fact when we put it in the strip board we have to do a break in the track between those 2 things, and in fact when I've made my little breadboard adapter here you'll see, maybe we'll see here, but there are a couple of breaks in the tracks. There's a break in the track there, break in the track there. Then we've got a wire moving the outputs over to the other side here. So basically I've got 6 pins out there, but the labeling of those is a little bit non-standard. I don't think they go 1, 2, 3, 4, 5, 6. They'll be a little bit random, but the best way I found to do this is put in a continuity tester into each one just to make and test the pin just to make sure you've got them the right way around. So that's my little PS2 breadboard adapter, and what I'm going to do now is to plug this into simple breadboard just with some pull-up resistors, and what I'll try and do is put in a logic analyzer on this just to check that the keyboards are working, and we'll also have a look to see if we can get a USB keyboard to actually talk PS2 with that green adapter I showed you earlier. Okay, so I've got my breadboard here. I've got my simpler of the logic analyzer. So this LA1010, the basic model, and it is fine for doing this particular exercise. I'm just going to plug this in so that the power lines line up. So at the moment I won't plug it quite in until I've put in the various pins. So I checked out which pins were which, and the ground pin is the lower one down here. The 5 volts is the one at the top here, and then the clock and the data are the next 2 lines. So I'm just going to plug in a pull-up resistor. So this is going to go from 5 volts to 5 volts to the clock, and we'll when I fit them into the breadboard properly, we'll put them in a proper, cut them down. But for the moment, so we've got two, I think they're 4.7k resistors, and when I first started looking at this, I thought I'd actually got a dead keyboard because I wasn't using these pull-up resistors. Wired up my breadboard and my connector, and basically we've got the ground plus 5 volts. This is the clock signal which we've got pulled up to 5 volts, and the data. I've then got the pin 1 and pin 2 of my logic analyzer connected to that, and then I've plugged in the PS2 keyboard, and all I'm going to do now is to turn on the bench power supply, and then what I'm going to do is to switch over to the screen share. So this is the logic analyzer. What I will just do actually is channel 5 red. I've got to trigger the logic analyzer when the power's turned on, so it will only start recording when the power's turned on. So we've got the logic analyzer set up, and we've also plugged in the channel 5, the red line, to the power supply so that I can trigger it on the power being turned on. And I've also got this analyzer. Now, the analyzers in this Kingsviz are quite clever. There's a lot of them. Most of them are hidden. I won't try and explain what all of these are, but the key thing is here I tend to be using the Parallel and Parallel 6800, but there's also PS2 keyboard mouse. So I've got the PS2 keyboard mouse, and what that does is says the clock is on signal 0, data is in signal 1, and it's a keyboard. So this should be decoding the keyboard signals. So all I'm going to do now is to switch it on. It's only going to do this for about 10 seconds, so we're sampling at 100 kilohertz. So the keyboard clock's fairly slow, and a million samples will give us about 10 seconds. So what we should see is initial power up message, and then I'll just press a couple of keys, perhaps 1 to 9, 1 to 0, and we'll actually see whether or not this is working. We've started analyzer, it's waiting for trigger, and now I'll just turn on the power. And now I'm going to press 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, enter. We'll just let that finish and see what comes back. Okay, that looks like it's working. So we can see here that if we go in to the initial power on, we drill down to here, we can see that in fact we've got a clock signal here, and the clock signal is a frequency of about 11 kilohertz. So you can see at the top right hand side here, frequency is about 11 kilohertz. We're not sampling this at a very fast rate, so the clock frequency is not that accurate. And then we can see here there's the data here. Now Ben Eater has explained how this data is encoded, so I'm not going to try and explain it here, but I think that the green there is the start bit, and I think that's the stop bit. Now the interesting thing is that rather than having to try and decode what all this sort of stuff is doing, we can see here that it said keyboard power on self-test successful 0 AA. So this is power on self-test, and I know from reading the data sheets that AA is the power on self-test. And we can also see down the right hand side here, it's a little bit small, but we actually get 2 signals for each key, make 1, break 1. And again, if you follow Ben Eater's video, you'll see that we actually get a break code with the key, make 2, break. So you can see here that the break seems to have an F0 in front of it. And I guess the reason why this is done is so that if you were holding down multiple keys, for example, in a game, then you'd be able to know that you've got multiple keys held down at the same time. And also with the Control, Shift and Alt keys, then those again are actually implemented in software. So it looks like it's working here. We've got the key codes coming out, and our logic analyzer is able to understand how this works. If we go in to look at the other key codes, this is where I was pressing the keys, and you can just see here that we've got the keyboard make, and then there'll probably be a keyboard break, which will be 2 bytes. So we've got the break code followed by the key that was let go. So that seems to be working. What I'm going to do now is just to record another one of these, but I'm going to press every single key on the keyboard. So I'm just going to go from left to right, top to bottom, and I'm going to collect the data for the whole keyboard. So now I'll just press the power. It started sampling, so I'm going to go through each key on the keyboard. So I'm going through the top row, all the function keys. What this should do is give us all the make and break codes for all of the keys on our keyboard. Okay, so that's all of them. I might have done the keypad enter key twice. Now we can see here down the right hand side that we've got all of these, and what I'm just going to do here is to export the data. I'll export in a CSV file, and we'll call it PS2 keyboard, all keys 2. Okay, so we'll have a look at that in a minute and we'll make it a little bit easier to see what's going on there. Let's have a quick look at that file. If we just make it a little easier to view, and we can filter as well. So if we go down, we can see that we've got power on self-test is successful. We've got escape, all the function keys, print screen, scroll lock. So you can see all looks pretty good. Keypads. So we've got some unrecognized keys there. So I think that's probably more to do with the analyzer software than anything else. We'll have a look at that in a bit to see what the unrecognized keys are. It's between shift left. It's probably the up arrow key, I think, at the moment. And there's also an invalid code. So there's a few things there that we might need to have a look at, and you can see I make and break enter key. Did I do the enter key twice? I may have done the enter key twice. Enter numpad, yes, I did enter numpad, did that twice. But anyway, you can see there that the codes for the majority of it all coming out, and they've all got a code. It's just the software hasn't necessarily converted the code into a text description. That may just be something where the KingSviz software needs to be updated. Okay, so that appears to work. What I'm just going to do now is do the same for the USB keyboard with the PS2 adapter and see if that works. Okay, so this is a PS2 keyboard with this converter. It is a mouse converter, but the pins for the keyboard and the mouse are the same. So we're just going to switch back to our KingSviz. We'll reduce the number of samples a little bit, and waiting for trigger. We'll now power this on and see if anything happens. And I'll press a couple of keys as well whilst we're doing it, just to see if anything's happening. Oh, no, in actual fact, it does look like we have got something. So in fact, if you do have one of these USB to PS2 converters, then it does look like USB keys do actually work. And if we zoom in on this particular bit here, we can see that this bit, so there was a bit of a strange bit there, so we didn't get the power on thing that we normally expect, but looks like we did get something. So might need to have another look at that just to see, but it does seem to be something, but it may not. This may just be random. I was typing in 1, 2, 3, 4, 5, 6, 7, 8, 9. So I do seem to get some of that, but some of the bit at the front looks to be a bit bizarre. So I'll have another look at that, but you do seem to get something out of it, but it may not be 100%, but you can always try that at a later date. So I did the test doing all the keys, and it looks like just at power on that it takes a second or two for the keyboard to decide that it's working in PS2 mode, and certainly the analyzer here is unable to work out what's going on. So you see that we've got a couple of things it doesn't recognize here, but I waited for about 5 seconds, then started typing in all of the keys that I did last time. So went along the top row, escape, F1, F2. So you can see that down the right hand side here that basically all of those things are largely working okay. I'll have a look and see whether or not some of the same codes are unrecognized, but here we go, we've got unrecognized keys around there, but it looks like the same ones. So it looks like the USB keyboard is also working. The only issue is you need to allow it probably a couple of seconds before trying to do anything with it, because it takes a little while for it to power on and decide that it's in a PS2 mode rather than USB mode. So I've updated the schematic diagram, and the chips we've got here now are the keyboard controller. There's a PLD that we're using for providing the read enable, write enable signals. We need an 8 megahertz oscillator to start with. Now, when I upgrade the CPU, there will be an 8 megahertz oscillator used for the CPU, but for the moment we'll just use this one here. And then we've got the keyboard socket down the bottom there. I've also done the wiring for the mouse, but I'm not going to enable this at the moment. And then the output buffers, so these inverters are actually open collector inverters, and these are used to actually drive the keyboard, and this is the reason why we need to include pull-up resistors. So although in the test I did earlier I used 4.7k resistors, the IBM PS2 Model 8 used 10k resistors, so I'm just going to use 10k resistors for that. And as far as all of the pins here, we've actually got the data bus. The sync pin is not actually used. We've got the write enable and read enable signals coming from this PLD, and I basically use the same rules that I use for the PLD in the digital analog converter for the video card. So it takes in the E clock signal, the read write signal, and generates the read and write signals here. And this is the chip enable signal for the CRTC chip. So if we go up to here, we can see that this is our decoder for the CRTC address range, and what I've done is I've used the Y4 output there, and I've just called that, this is the Y3 key, because this is actually decoding the Y3 signal here. So this Y3 is then broken out into all of these other ones, so I'm just calling this Y3 key for the moment. And so what that means is we'll get an address in the D000 range that will be used for accessing this. Then there are a number of pins that the datasheet tells you either to tie to ground or to 5 volts. So TLEA is tied to ground, SS to 5 volts, as are the TH prog and TH SSSP. Those are related to, I think, programming the microcontroller and the original ones. And then because we're using an 8 megahertz crystal coming in here, we just tie the other crystal input to ground as well. The most tricky bit here is making sure you don't make mistakes with the P10, P11, P20, P21. So these are the port numbers, and it's important not to get confused with the pin numbers, which I did on a couple of occasions. And the pin layout for this is a little bit complicated. So you can see here that we've got the keyboard data and keyboard clock coming from P27 and P26, and that the test 0 comes round to the keyboard clock, and that the P10 comes round to the keyboard data, and this is used by the keyboard controller when it powers up to determine if it's running in PS2 mode or it's running in the AT mode. So I've made sure all these sort of connections are coming through correctly. And then the wiring up to the keyboard port. So we've got the clock comes out to pin 5, and we've also got the capacitor here, and we've got the keyboard data comes out to pin 1, and we've got ground, and we've got 5 volts. Now this mouse connector I won't install at the moment, because in testing this we're going to need to shuffle the chips around once we've taken out the 8 megahertz oscillator and things like that, so there'll be a bit more space to be able to add the mouse port in there. And there's also 2 outputs here which are referenced in the data sheet, which are basically used for triggering interrupts, particularly used on Intel 8088 upwards machines. For the moment I'm just going to be polling this chip for input, a bit like we do with the PIAs for the current keypad. So I'm not going to make use of the interrupts for the moment, but I will wire them up. So that's pretty much it. All we need to do now is to wire this up on a breadboard, and then we're just going to have to hook in the data bus, address 0, the read write signal, e-signals and reset, and a few other things. So once those are actually wired in, then we should have this up and running, and then we're just going to need to write the software to initialize the keyboard controller, and then to be able to poll the keyboard values to see whether or not we can get anything out of it. Okay, so I've completed the schematic and I printed it out. Unfortunately the chip here is the ground at the top there and VCC on the bottom, which is the opposite way around to the way the labels come out. But what I want to do is to keep the data lines on this side, and obviously the CPU related signals on this side, and it's going to go off to the main Nanocomp board up here. And so I've changed the connector around so that the PS2 cable's going to be coming in from the bottom. So effectively this board will go underneath the current Nanocomp bus arrangement here. So the buses will go up here and the keyboard will come down here. So I figured that would be a better layout. So I've just sort of approximated the chip layout. So this is the keyboard controller. So just going to plug that in. This is the 8 megahertz clock. And again, I'll push that in once I've confirmed where the pins are. This is our PLD that provides the read and write signals. And then this is our open collector buffer that provides the output for driving the port up there. So I've left more space on this side because this is where all the wires that are going to be coming around and going up to here and here. So I figured I'd need more space on this side, and the buses here should be a lot more straightforward to hook up to. So what I'm going to do now is to go through and check everything off the diagram as I go. So just going to plug in the power lines and decoupling capacitors, the power for the crystal, then wire in the output of the crystal. We just need to tie the other crystal to ground. Check those off. So then these are the other rails that need to be tied to +5 or to ground for the programming inputs to the microcontroller. Check those off. Then we're going to put in the power lines for the other chips. Check those off. So I'm not going to do the mouse gates at the moment, the mouse connector. Now we need to put the pull-up resistors for the output and the clock, the data and the clock. Check those off. Going to wire in the outputs from the 24 up to the inputs to the clock and the data gate that's on. The first one's the IRQ, I think. We actually put the resistor in the wrong line initially. It's in the right one now. Then the test 0 output, feedback. Okay, now we're just plugging in the P10 output for the other feedback. So just put in the capacitors on the output to the PS2 connector, and then wire in both the data in out and the clock signals. Right, so now we need to hook up the PLD. So that's the chip enable signal coming from the Y3 signal. That's the read and the write lines. They make use of the read, write and E signals. So now we're going to plug in the data cable connector and the reset. And then we've also got the read, write and E signals. As I was going through the datasheet, you can see I've highlighted a lot of the key elements here. I realised that by omitting the mouse connections, mouse support connections, that in fact the check that it does to see whether it's in AT mode or PS2 mode, in fact checks both the test 1 and the P10 line. Now the P10 line is already connected here, but the test line here will be going over to this side, so I'm actually going to have to connect up the mouse side of things, otherwise it won't detect that it's in PS2 mode properly. So all I'm going to do is to wire in the rest of the bits that I crossed out previously. So what I'm going to need to do is put in these two resistors to pull up the outputs, and then I'm going to be wiring in the interrupt request line, the clock line, then the data line to the pins over here. So I thought I was saving myself some bother there, but in fact I think it would have resulted in some really difficult to track down problems. So I'm just going to put those in now. So we're just going to put in the pull-up resistors for the data and the clock. Tick those off. Then I'm going to wire in the feeds to the interrupt. And then the clock and the data outputs. Now we need to include the feedback down to P11, I think it was. Then finally the test 1 feedback, which is the thing we need that was missing. And we just put in a couple of decoupling capacitors as well. Okay, so I've fitted the board and I've wired all of the various cables in. So these are the data lines are going over to the data ports. We've got the reset, the read-write line going over here as well. And then we've also got the CRTC enable signal, which is going over to our CRTC address decoder over there. So this is given the D600 range here. And then I've also then put in the logic analyzer here so we can actually see some of the signals. When I was testing this out, the only problem I really had with this was that my 8 MHz oscillator here was not providing very good voltage levels, and it was not enough to actually drive the TTL. I suspect I may have connected it up the wrong way around in the past and probably damaged it somewhat. So all I've done compared to the original schematic is I've just replaced this oscillator with a basic crystal and 2 capacitors as per the data sheet. So that's pretty much it as it was. We're now plugged in the keyboard, so I've got my PS2 keyboard to the left hand side here. And what I'm going to do is to quickly show you the test software that I've done, and then we'll go in and fire it up and see if we can get something out of the PS2 keyboard. So there's quite a lot of information out there to explain how the keyboards work. The IBM PCAT technical guides include quite a detailed section on using the keyboard. I'm not going to go through it in great detail, but needless to say, the IBM documentation is fairly thorough. One of the things that confused me is that there's 2 lots of commands. There's one lot of commands for talking to the 8042 compatible controller, and there's another load of commands that are passed through the controller down to the keyboard. So there's actually a set of commands that the keyboard understands as well. And when dealing with the initialization of the keyboard, you need to be clear between whether you're dealing with a controller or you're dealing with the keyboard device itself. Something that I got confused with when I was first doing this. So there's a lot of information here about all the different operations, all the different things you can send the keyboard, information about interacting with it. There's also, in the original XT documentation, there's information in the BIOS about interacting with it. And the key thing really about this is that what you get from the keyboard is a scan code. You don't get an ASCII value directly matching, say, a letter A or a letter 1 or something like that. What you have to do is actually decode the scan code and then produce the appropriate ASCII value. And for those keys where there isn't an obvious ASCII value, so for example the page up, page down, home, end, up and down arrow keys don't have an ASCII equivalent, and so there's an encoding scheme which IBM have defined for doing those extended characters, which you'll come to a little bit later. But needless to say, this was a lot more complicated to get your head around than I had initially anticipated, and with the PC-80 and PS2 onwards, there's even 3 sets of scan codes just to make things more interesting. Now, in order to do this, what I helped to simplify things was I actually looked at this 8088 BIOS from Sergey, he's still publishing this. So this is a BIOS being developed for sort of Intel 8088 compatible XT single computer type boards. And this includes quite a lot of information on how to initialize a keyboard. So I've helped this. This is all in Intel 8086 assembly language, so it isn't directly usable. But we can see here with the BIOS that, for example, the interrupt 9 is the keyboard interrupt generally on the IBM PC. So what I've been able to do is to take some guidance from here. So the keyboard include file here has the keyboard interrupt handler, and this is what basically does most of the manipulation of things like shift keys, numlock and all that sort of stuff, and also calls the decoding information. There is also then an AT keyboard specific sort of routine here, and this is the same as PS2 as well, and this has a number of routines which I've used to kind of direct myself towards writing C code on 6809. So there are things like sending a command with an argument, which normally goes to the data port, writing data to the data port, and reading data from the data port. And there's also a couple of other things we have to do for waiting until certain status codes are at the right value before we can send data. There's a few routines in here to do with the auxiliary port, or the mouse port as it would be known, but I'm not doing anything with that at the moment. And then finally we get down to the initialization, and this is really where the meat of everything does, and this is where we're sort of testing the keyboard controller, testing the interface, resetting it if it's needing it, and doing various other commands and things. So I'm not going to go through all that lot in detail here, but I've used that to drive the code that I'm doing. So the code that we're going to be using for testing this is quite a simple derivation from the 256 color test that I was using before, and the main reason why I've got it is I need to initialize the CRTC and the palette, the VGA palette, before I can do anything here. And the main guts of it is actually the keyboard initialization, and then I have got a couple of tests here where I'm sending an echo command. I'm also setting the LED status on the keyboard before then just reading the individual code from the key in a loop for up to 500. I think I've done this for the moment. I have been playing around with the different scan code sets, but I won't talk about that for the moment. The default scan code that we saw earlier is actually scan code set 2, which is the one that provides a make code and then an F0 break and then the scan code for the key, and we'll be seeing that when we look in the logic analyzer. This code calls the nanocomp library, and the nanocomp library now includes equivalents of these commands, so flushing the keyboard input buffer, sending command, writing command. So these are very similar to the functions that were in the BIOS routines. I've just rewritten them to work in C and use the address decoding for the nanocomp. So we've got all these routines, and then we've got the initialization. You'll see there's quite a lot of printf debug statements, and this produces quite a detailed log on the serial port, which I can then look at in a text editor, which we can then use to review this. So basically what it's doing is initializing the keyboard, testing it, making sure everything's okay, and then sort of leaving it in a state, hopefully, that we can do things with it. So in particular, setting the configuration bits and things. And there's one particular thing I need to come to here, whether or not we have IBM scan code PCXT-AT translation, which I'll talk about in a little while, but we don't need to worry about it for the moment. So that's the code. I'm just going to compile the latest version of the code. There's a few warnings. We don't need to worry about that too much. I've just switched on the nanocomp. I will put it into load mode. I'm just going to send down that test program. Once that's down, I'm just going to run the logic analyzer so we can capture any output. So that's completed. And we'll just get ready to run that. And the terminal, I'm just going to capture the output so we can actually see what's going on there. And then we'll put the logic analyzer ready, and I'm just going to run this now. So hopefully that's running. And when I see the keyboard lights flash, I'm just putting some keys in. So I'm doing a few D, E, F, and perhaps. Okay, so let's have a quick look and see what's come through. So just stop the capture and we'll have a look in the capture.txt. So we can see that there's quite a lot of the debug information here, but we can see where we're sending various commands. We're running the self-test. The self-test is okay. So in the keyboard self-test, disabling things, re-enabling them, there's actually an echo command here where we send an EE and we get an EE back. And then there's the writing to the LEDs, and then down here we can actually see where I've started to type in some of the numbers. So we've got code 02, and 82 is in fact the break code for 02. Now the interesting thing about this 8242 chip is that it translates from later versions of the AT and PS2 keys into the legacy XT. And in fact, the BIOS routines that are actually looking at here, in fact, these BIOS routines, these are actually using legacy codes. So I decided that I would actually keep it in legacy mode because it would mean that the lookup tables in here I could actually use. This means that we're actually getting the individual codes. So we've got a make code and a break code. And if you see down the bottom here, we should see some of the other ones. So we should be able to look up these values in the various IBM documentation scan codes. Should be able to work out, oh yeah, that was the A key or the B key. Now what I'm going to need to do now before I can actually display the real characters on the screen is to actually be able to look into this scan code logic and actually implement that so we can output the ASCII codes to the screen. So let's just have a little look at the logic analyzer to see what's coming out here. So what we've got here is where we're writing to the keyboard controller and reading to it, and these signals are only applicable when the Y3 key select signal is low. And we can see up here that in fact these are the keyboard PS2 decode. So this is traffic going backwards and forwards between the controller and the keyboard. So if we zoom in to one of the first writes down here, we can actually start to see some of the commands that we're sending. So one of the first ones is going to be 60, which basically says write a status byte to the data signal. So we can see here that A0 is 1, so this is going to the command register. And if we look at what the next write is, we should see that that should be a value which I think is 70. 70, yes. So 70 is the write, and you'll see here that A0 is now 0, which means it's going to the data port. So that's the first bit of the initialization where we're disabling the keyboard controller initially, and you'll see here that in fact the clock signal goes low, which basically means the computer has disabled the interaction with the keyboard controller. We do various other things here, and what this is doing is sort of interrogating thing, running some tests, and then I think what it will be doing is initiating a reset keyboard. So it's initiated reset keyboard with an acknowledgement coming back from the keyboard. Then we need to wait a little while because it can take a little while for the keyboard to actually come out of reset. And so what the code here does is waits for a little bit, and then we can actually start to interact with it again, and we'll see that we've got a disable test. Then there should be re-enabling the keyboard. So these are keyboard commands, not controller commands. So these are going down to the keyboard. And then we've got our echo test where we're sending the EE echo and the keyboard's echoing that back correctly. Then there'll be some commands, I think, here for setting the LEDs. Yep, so we're setting the LED. So this is set LED, acknowledgement, and then the next one will be setting the values, which 7 is 111, which turns on all the LEDs on. So that's working, and then we should then be able to then see the characters in the keyboard that I waited until the lights had turned on. Then I started typing characters. Now what we'll see here is by default the keyboard goes into scan code 2 mode. So the first one that I pressed was the number 1, and that you can see here that I'm getting that make 1 0x16, so that's 16 hex, and then the break code we can see is F016. But if we go and have a look in the log file that I've actually got in the code, that we'll see that this has not actually resulted in this code coming in. What we've actually got is, for this first one here, we can see that we've actually got code is 02 and then the break code is 82. And the reason for that is that what is happening is because one of the configuration bits in our setting up the keyboard controller, so in particular this enable scan translation, what this basically does is takes the AT style scan codes and converts them into PC. And so in fact we've actually got it set to 1 at the moment. And what that means then is it's converting it into this older style code. But the advantage of that is that the BIOS scan code conversion will actually work with that. And so what I'm going to do now is to go and look at updating the software to do that scan code conversion. But I think what I'll do is I'll break the video now and we'll come back in another video to actually look at the software for the scan code conversion, because it's quite complicated. So what that's shown is that we're able to get our scan codes from the keyboard, and that the AT style ones will be converted into the XT style scan codes. And for evidence, the turning on these lights, the LEDs, has been done via the code here, and we've also seen as we typed in the keys that those are appearing in the log file. So what I'm going to do is to break the video now, because to be honest, most of this is now software rather than hardware. The hardware appears to be working. So apart from the problem I had with one of the crystals, then we've managed to get the hardware support for the keyboard. A lot of the C code is stuff that's going to be going into the Nanocomp monitor rewritten in C. So this is going to be something that's going to be going along in the background. And I would say is that the conversion of scan codes and the way how numlock, caps lock is all quite complicated, and it's going to take a little while to work out. So the hardware seems to be working okay. So thanks for watching. If you found it interesting, please hit like, and if you don't want to miss out on future videos, please hit subscribe. In the next video, I'm going to be looking at adding sound support and taking an analog joystick and getting some digital signals out of it, and that's going to allow me to be able to add sound into some of the games that we've already done using the video controller in earlier videos. So I'll be looking at some point in time and updating those, perhaps to make use of the sound and the joystick. Thanks for watching.